Welcome to this deep dive. We're digging into p-values today, something you asked us about, and yeah, something you see everywhere in research.
Absolutely. They pop up constantly.
We want to unpack what they really mean, what affects them, and maybe why they aren't the final word on understanding data.
Right. It's more nuanced than just a single number.
So we'll use some key questions as our guide, our mission.
Oh,
They
wow.
give you a clearer, more useful handle on p-values so you can look at findings with, well, a bit more confidence.
Let's do it.
Okay, first things first. What actually is a p-value?
Okay, so the p-value is basically the probability. It's the chance you get the results you saw in your study, or results even more extreme, if the null hypothesis were true.
The null hypothesis meaning, like, no real effect, no difference.
Exactly. The assumption that there's nothing really going on.
Yeah.
So a small p-value means, wow, this data would be pretty surprising if there's truly no effect.
Right. Okay, so it hints that maybe that no effect idea is wrong. Got it. Now, how does study size, sample size fit into this?
Oh, sample size is crucial. It has a really big impact.
How so?
Well, with a really large sample size, even a very tiny, almost trivial effect can end up looking statistically significant. It can push that p-value down.
So you get a p less than 0.05, but the actual difference is minuscule.
Precisely. And conversely, a small study might totally miss a genuine important effect simply because it doesn't have enough statistical power. You might get a large p-value even if something real is happening.
Okay, so that brings up practical significance versus statistical significance. That tiny effect in the huge study might be statistically significant, but maybe it doesn't matter in the real world.
Exactly right. That's a key distinction.
Yeah.
A p-value might be tiny, strong statistical evidence against the null.
Hmm.
But the effect size, the actual magnitude of the difference, could be practically meaningless.
Like a drug lowering blood pressure by half a point technically works, statistically speaking, but
Yeah,
so what?
yeah, that kind of thing. It's easy to get fixated on the p-value and forget to ask, is this effect big enough to care about?
That makes sense. Okay, what about those close calls? Say alpha is 0.05, the standard cutoff, and the p-value comes out as like 0.052, just over the line.
Yeah. The borderline result, it's, well, it's not necessarily a failed result.
But it's not significant.
By that strict zero point zero 0.05 rule, no. But 0.052 means the evidence against the null is weak, not necessarily absent. It could hint at a real effect that the study maybe wasn't quite powerful enough to nail down definitively.
Maybe needed more participants.
Could be. It definitely argues against rigidly worshiping that 0.05 threshold. It's somewhat arbitrary, really. You should consider the context.
Okay, so relying only on p-values seems shaky. What are the big pitfalls? You mentioned it doesn't prove our hypothesis is right.
Right. A big one is that it tells you nothing about the size or importance of the effect. And then there's the multiple testing problem.
Yeah, running lots and lots of tests in the same data set.
Exactly. If you test enough things, you're bound to find something that looks significant just by random chance. Pure luck.
Like flipping a coin enough times, you'll eventually get a weird streak.
Kind of like that, yeah. Each test carries a risk of a false positive. Do loads of tests, and your overall chance of getting fooled by randomness goes way up. It's something you really need to watch out for.
Okay. What about different types of tests? Two-tailed tests. How does the p-value calculation work there?
So a two-tailed test looks for an effect in either direction, an increase or a decrease. The p-value reflects that. It's the probability of seeing data as extreme as yours, or more so in either tail of the distribution.
Gotcha. Covers both possibilities. And non-parametric tests still use p-values.
Yep, the core idea is the same. Probability under the null. But the calculation is different because non-parametric tests make fewer assumptions about how your data is distributed.
And how does the p-value connect to the actual test statistic itself, like the t-value or f-value?
Think of the test statistic as measuring how far your data deviates from what the null hypothesis predicts.
So a bigger deviation means a bigger test statistic?
Generally, yes. And usually, a larger test statistic corresponds to a smaller p-value. It means your results are further out in the tail of the distribution, making them less likely under the null.
Okay. Final question. Sometimes you just see p 0.001. What's that about?
That just means the calculated p-value is really, really tiny. Less than 1 in 1,000.
So very strong evidence against the null.
Statistically speaking, yes. But it's just a shorthand. They're saying it's so small the exact tiny number isn't that informative beyond indicating high significance. Still doesn't tell you about practical importance, though.
Right. Okay, this makes a lot more sense. So summing up, p-value is about how surprising the data is if there's no effect. Sample size matters a lot. It's not the same as practical importance, and we need to be cautious, especially with multiple tests.
That's a great summary. It's a tool, a useful one, but just one piece. You need effect sizes, context, study design quality, the whole picture.
So, the takeaway for you listening, next time you see a p-value, think about how it might be interpreted or maybe misinterpreted. Ask yourself, what else is important here besides just that statistical number? Something to chew on. Thanks for joining us for this deep dive.